Have you ever wondered how functions can call themselves, or why recursion is such an essential concept in programming? Today, we're going to be breaking down recursion, a fundamental topic in data structures and algorithms. Hey everyone, welcome back to the Tech Tutor. In this video, we'll be exploring how recursion works, when to use it, and why it's so powerful. Let's get started. So, recursion is when a function basically calls itself to solve smaller and smaller versions of the same problem. It's an elegant way to simplify complex problems and is widely used in programming. You'll see recursion in many places, like sorting algorithms, merge stored and quick stored, tree traversals, and even AI pathfinding. But before we get into real world use cases, let's break down how recursion actually works. The key to recursion is understanding its two main parts. First part, base case, and the second part is the recursive case. So the base case tells the function when to stop, preventing infinite loops. The recursive case, on the other hand, is where the function calls itself to keep solving smaller problems. Let's take an example, computing the factorial of a number. So this is what a factorial function looks like. So if we call factorial of 5, it keeps calling itself, if you look at the code over here, until it reaches the base case factorial of 0, which returns 1. Then it multiplies each returning value back up to get the final result. To kind of trace this, so let's see what happens if we put 5 over here. Okay, so factorial of 5. So f factorial, but I'm going to call it f of 5. So it's going to go over here, and 5 is not equal to 0. Okay, so it's going to return 5 times factorial of 4. Okay, factorial of 4 is going to go up. I'm going to create a box so that it doesn't get confusing. Factorial of 4 is going to go up, and then it is still not equal to 0. So we're going to keep doing that until we get 0 in our parameters. So I hope you see how the function is calling itself over here and over here. Okay, so this is going to keep on going. Factorial of 3. Oops, our leaning tower of Pisa. Let me make sure. Try to make sure we don't. No, so factorial of 3. Factorial of 3. 3 times f of 2. Then f of 2 is going to give us, and then it's going to be 2 times f of 1, and I'm going to put it over here. So f of 1 is going to give us 1 times f of 0. Now see, we've gotten 0 over here. So if now n is equal to 0, this is going to, our base case is going to come into picture. So it's going to be 1 times 1. Okay, it's going to return 1. 1 times 1 is 1. Okay, now this is the part of recursion that we should remember. So 1 times 1 is 1. It's going to go back over here. 2 times 1, right? Because f of 1 is going to be 1. 2 times 1 is 2. That's going to go down. 3 times 2 is 6. That's going to go down. 6 times 4 is 24. That's going to, then now 24 is going to go down. 24 times 5, what is that? 24 times 5 is going to give us 120, guys. So the answer to this call, right, is 120. So basically what that did was that 1 times 2 times 3 times 4 times 5. Okay, and this is what we call, if you didn't know what factorial is, this is what we call this doing a factorial of a number. So factorial of 5 is 120, guys. Okay, so now let's get back to our slides. I'm gonna go back to my cursor. Present. Let me just go back to my slide, the slide we were on. Okay, now before we go into this method simplifies many problems, but it also introduced some challenges such as stack usage, which we will discuss next. So understanding the called stack. So every time a function is called, it's stored in memory inside a storage structure called the call stack. Okay, kind of like the stack I kind of did before. Like it's kind of like a called stack you see over here. Okay, so this is called, this is called, this is called, and then after you get the answer, it goes down, the value goes down. Okay, so each function call waits for the next one to return before it can complete. This is why recursion can use a lot of memory, guys. And if the recursion depth is too high, we could get a stack overflow error. So when should we use recursion and when should we avoid it? So let's compare recursion to iteration. Iteration is what we do using for loops, and it's something you might be familiar with more than recursion. So recursion has a high memory usage, right? It uses more memory due to the called stack. While recursion makes certain problems more intuitive, iteration is often more efficient. Okay, so they both achieve the same results though. Yeah. Now let's see where recursion can be useful. Some applications of this. Some common recursive problems. Okay, Fibonacci calculation, Fibonacci sequence, right? Factorial calculation. Actually, sorry, factorial calculation is what we did in the slide of the code. Sum of digits, reversing a string, and a problem known as Tower of Hanoi. Okay. Now let's take an example where recursion can be improved using memoization. So this is called memoization, guys. One downside of recursion is redundant calculations. In problems like Fibonacci, the same values get recalculated multiple times. So what memoization does, it stores these results to avoid unnecessary computations, making recursion far more efficient. Okay, so it kind of stores those values, as you can see over here. Okay, but recursion isn't just useful for numbers, guys. It plays a huge role in data structures too. Coming to sorting algorithms, quick store recursion. Okay, so what it's widely used for tree traversals, searching in graphs, and implementing divide and conquer algorithms like merge sort, quick sort. Understanding recursion, guys, it makes solving these types of problems much easier. Okay, now let's talk about a special topic of recursion called tail recursion. Tail recursion is when the recursive call is the last operation in the function, allowing some compilers to optimize it and remove some extra stack frames. So what this does is this reduces memory usage and prevents stack overflow. While C++ doesn't always optimize tail recursion, languages like Python and Lisp do. Coming to the conclusion, recursion is an incredibly powerful tool in programming, but it should be used wisely. The key is knowing when recursion simplifies the problem and when iteration would be a better alternative. Guys, I hope this helped you understand recursion better. If you found it useful, guys, don't forget to like, comment, share, and for more data structures and algorithms videos. Thank you for watching. Leave down a comment if you have any questions, and I'll see you in the next one.